Welcome back. We're going to finish off our Anova uh, video here with the follow-up to what we did before. I still have the data on the screen from that, and as you recall, we ran an Anova, and we've got a lot of data, the most important being the p-value. P-value is less than 0.05, so we conclude that there are differences, or at least one difference, in all of this data. At least one of these treatments is different from at least one other. They could all be different from each other. Again, there may be groups, and that's what we have to go forward to do to figure out exactly where those differences lie in this data. So so an ANOVA actually is an incomplete test because all it tells you is yes, there are differences, and you really want to know, which is best. So you got to go on and do something called a mean separation. And this is called a Tukey test. There are a number of different mean separation tests. Tukey was a statistician. He was famous. He gets a test named after him, whatever. But anyway, it's a very simple one, and I've actually made this Excel spreadsheet very simple for you to do one. And so again, here's our data. It's the same data that we had on the previous page. Here is our Anova result. It's exactly the same as we saw on the previous page. I just put it here for convenience. And there's a little 5-step process here to do a Tukey mean separation test. Okay, and this is going to tell us, where the differences lie. And we need some data from the Anova, specifically the p-value and this little gem right here. This is called the error mean square, and it's at the intersection of the within groups row and the MS column. So let's just read along. It's color-coded for your convenience. So if the p-value is lower than 0.05, then proceed. Okay, well, we know that it is. Copy the number given in the Anova table right where I told you before, highlighted here in yellow. So we would just come here, if it wasn't already there, put that in. Don't worry about the standard error out here. That's part of the calculation that it needs. You don't have to mess with that. Then the red cell, we need to know the number of treatments in the experiment. In this case, it was 4. It was, remember, untouched, brushed, rubbed, and shaken. And then in this cell, we want to tell it how many samples. And if you go back to your data, there's 1, 2, 3, 4, 5, 6 samples in each treatment. So we go over here and we put a 6 in, and we get something that I used to call the yardstick. It's actually the Tukey statistic, 16.2. So what this is telling us is that any two means that we get, okay, and here are all the different means in this study right here, the average for the 4 treatments. Any two that differ by more than that amount are different. Any two that differ by less than this amount are not. Okay? So basically we can do all possible combinations. Here's the means. Here's the treatments. So I arranged them in order here, descending order, 85, 76, 72, 62. So what are all the possible combinations of differences? And so 85 less 76 is 9. I would conclude that untouched and rubbed are similar because the difference, 9, is less than the Tukey statistic, 16. It has to be 16 or more to be different. So again, let's do the next one. So 85 less 72 is 13, still less, no difference. 85 less 62 is 23, that's more. So we know that the untouched is statistically taller than the shaken group. That's what we know at this point. And then we go on and do the rest of them. Now we have to do, rub versus brush. We haven't done that yet. There's only 4 units different, not different. Rub versus shaken, 14 units, close, no cigar. And then finally, brushed versus shaken are 10 units different between the 72 and the 62 here. Again, less than the standard amount the Tukey statistic tells us to look for. And so really there's only one difference in this entire experiment. That is that the control, the untouched, were taller than the shaken. And so we would therefore conclude that the shaken is in fact the best treatment to use.